Hello everyone, welcome to MindMatrix. So here we are with another lecture on operating system, and today we will be covering some more CPU scheduling algorithms like longest job first, LRTF, HRRN, and round robin CPU scheduling algorithm. So let's start the video. So this is my introduction. I hope you are aware of it now. So let's skip it and yeah. So you can join our doubt discussion telegram group. This is the QR code which you can scan and you will be able to join it. There you can ask your queries, your doubts related to our, the concepts or any question if you have, you can ask there in our group. Okay. And do share, do like and subscribe to our Mind Matrix YouTube channel so that you don't miss any notifications in the future also. So let's start. So today we will be starting with longest job first. We have covered few CPU scheduling algorithms in the previous lecture. So here we will be first talking about longest job first. As the name suggests, the process which is having the longest burst time, we are going to schedule that process first. Okay. So LJF, a CPU is assigned to the processes having largest burst time. Okay. And in case of a tie, it is broken by FCFS, first come first serve. Now in case of longest job first, again we have two modes, non-preemptive mode and preemptive mode. In case of non-preemptive mode, it is simply LJF, that is longest job first. In case of preemptive mode, it becomes LRTF, longest remaining time first. Longest remaining time first. So as in the previous lecture, we have seen SRTF, shortest remaining time first. So it is similar to that. In SRTF, we schedule the processes having the smallest burst time. Here we are going to schedule the processes having largest burst time, but it is going to be preemptive in nature as compared to LJF. Okay. Now, what are the advantages? No process can complete until the longest job also reaches its completion. Clear? And it is quite obvious also. First we are scheduling the longest job first, so it is not going to happen that the process which is having smaller burst time is completing first before the process which is having longest burst time. All the processes approximately finishes at the same time. So we are going to see some examples also. Before that, let's see the disadvantage as well. So this LJF is having the average waiting time is going to be high in this case because we are scheduling the processes which are having the longest burst time. So the processes which are having smaller burst time, they have to wait. So, and due to that, the average waiting time goes high. Second one is processes with smaller burst time may starve for CPU. Starvation may occur in this case. Now let's see the example. So here we have 5 processes from P1 to P5 and the arrival time is given to us. The burst time is also given to us. We need to find the completion time of all the processes, turnaround time and waiting time. Okay. So LJF is non-preemptive in nature. So let's make the Gantt chart and let's schedule the processes here. So at 0 units of time, do we have any process present in the ready queue? So if you see carefully, yes, P1 is present at 0 units of time in the ready queue. So we can clearly schedule that process first because there is no other process. So we don't have to compare now. So P1 we can schedule, and as it is non-preemptive in nature, that means we have to schedule for the entire burst time. So for 3 units of time I can schedule. So 0 plus 3 it is going to be 3 and I can make it 0. Now at 3 units of time, you can see P2 has arrived. So P1 has completed its execution. So at 3 units of time, P2 has arrived, P3 has arrived, and P4 has also arrived. Till 3 units of time, these 3 processes are now present in the ready queue. So now we need to compare the burst time. So if you see here for P2, the burst time is 2, for P3 it is 4, for P4 it is 5. So P4 is having the longest burst time as of now in these 3 processes, among these 3 processes. So we are going to schedule P4 first. So for entire 5 units of time we are going to schedule. So 3 plus 5 it is going to be 8 and we can make it 0. P4 has also completed its execution. Clear? Now at 8 units of time, okay, so at 8 units of time P5 has also arrived because the arrival time of P5 is 4. Now we have three processes P2, P3 and P5 present in the ready queue. Again, compare the burst time of all these three processes. You will find it out that P5 is having the largest burst time, that is 6. So I can schedule P5 process first. So 8 plus 6, it is going to be 14 and we can make it 0. P5 has also completed its execution. Now we have P2 and P3. So if you compare, P3 is having the larger burst time as compared to P2, that is 4 units of time. So 14 plus 4, it is going to be 18. We can make it 0. P3 has completed its execution. Now we have just only one process left in the ready queue, that is P2, and we are going to schedule P2 now. The burst time of P2 is 2 units of time, so 18 plus 2, it is going to be 20. We can make it 0. P2 has completed its execution as well. So all the processes have completed their execution. We can write the completion time here. So for P1, the completion time is 3. For P2, it is 20. For P3, it is 18. For P4, it is 8. For P5, it is 14. What is turnaround time? We know this from the previous lecture as well. Turnaround time is nothing but completion time minus arrival time. Clear? So completion time minus arrival time, 3 minus 0, it is going to be 3 here. 20 minus 1, it is going to be 19. 18 minus 2, it is going to be 16. 8 minus 3, it is going to be 5. 14 minus 4, it is going to be 10. What about waiting time? We know waiting time is nothing but turnaround time minus initial burst time. So this is going to be the waiting time, right? We have seen all these formulas in the previous lecture as well. So waiting time, we can find it out. 3 minus 3, it is going to be 0. 19 minus 2, it is going to be 17. 16 minus 4, it is going to be 12. 5 minus 5 is 0. 10 minus 6, it is 4. So now we can find the average turnaround time, average waiting time as well. Clear? So in this way, we can schedule the processes using longest job first, which is a non-preemptive CPU scheduling algorithm. Clear? So now let's solve this question based on LRTF, that is longest remaining time first. Which is preemptive in nature. Longest remaining time first, right? So let's schedule this process, all these processes using this algorithm. So at 0 units of time, we can see there is no process that has arrived in the ready queue. So we can say for 1 unit of time, the CPU will remain idle because the next process, the first process is going to arrive at 1 unit of time. So CPU will remain idle for 1 unit of time, right? Now P1 arrived. As there is only one process, so we can schedule it for at least 1 unit of time, right? So if we schedule it for 1 unit of time, here we are going to get only one burst time, 1 unit of burst time is remaining now for P1. Now at 2 units of time, P2 has also arrived. So we can compare the burst time of these two processes. P2 is having the longer burst time, so we can schedule P2 first, right? So we can schedule it for 1 unit of time. So here we are going to get 3. Now at 3 units of time, P3 has also arrived. So we can schedule P3 process now. Okay. So if you see here, for 1 unit of time, we are going to schedule it. So here we will be getting 5. Now at 4 units of time, P4 has also arrived. And you can see P4 is having the longer burst time, the largest burst time. So we can schedule P4 now for 1 unit of time. So this is going to be 7. Still we have P4 which is having the largest burst time, so we are going to schedule it, let's say for 1 unit of time, we are going to get 6. Now we can further schedule P4 again for 1 unit of time, so it is 7. We can make it 5. Now if you see here, there is a tie between P3 and P4, both are having 5 units of burst time, so we are going to schedule P3 first because that arrived first, right, based on FCFS. So we are going to schedule P3 first for 1 unit of time. It is going to become 1. I mean, it is going to reduced by 1, so we will be getting 4 now. Now we can schedule P4 process for 1 unit of time. It is 9. We can make it 4. Now again we are going to schedule P3 process for 1 unit of time. It is going to become 3. then P4 process, it is going to become 3. Now, now three processes are having the same burst time, P2, P3 and P4. So first we are going to schedule P2 process first now, based on FCFS. So if we schedule P2 process for 1 unit of time, it is going to become 2. Then we can schedule P3 again, 13, it is going to become 2. Then P4 for 1 unit of time, it is going to become 2 again. There is a tie between these three processes. So we are going to schedule P2 again for 1 unit of time, it is going to become 1. Then it is P3 for 1 unit of time, then it is P4 for 1 unit of time. Now there's a tie between all the four processes. All the processes are having 1 as the burst time, remaining burst time. So we are going to schedule all these processes one by one based on first come first serve. So P1 arrived first, so it is 18, make it 0. Then it is P2, 19, make it 0. Then it is P3, 20, we can make it 0. And then it is P4, 21, we can make it 0. So you can see almost all the processes finishes at the same time, almost at the same time, approximately we can say. Right, so in this way we can schedule all these processes using longest remaining time first. Now we can write the completion time of all the processes as it is preemptive in nature. So always keep in mind, for preemptive CPU scheduling algorithms, always start from a right hand side, go from right to left in order to find the correct completion time, because you may miss out if you go from left to right. So for P1 it is 18, right? So we can write 18 as the completion time for P1. For P2 it is 19, for P3 it is 20, and for P4 it is 21. Clear? So this is the completion time of all these processes. We can find turnaround time. Turnaround time is nothing but completion time minus arrival time. 18 minus 1 it is 17, 19 minus 2 it is 17, 20 minus 3 it is 17, 21 minus 4 it is 17. So turnaround time is same for all the processes here. Clear? Now what about waiting time? Turnaround time minus burst time. 17 minus 2 it is going to be 15, 17 minus 4 it is going to be 13, 17 minus 6 it is 11, 17 minus 8 it is going to be 9. So we can find the turnaround time, it is going to be same, that is 17 average turnaround time, and we can find the average waiting time as well. Clear? So in this way we can schedule the processes using longest remaining time first CPU scheduling algorithm. Okay, so let's proceed further to our next algorithm, that is HRRN, which is nothing but highest response ratio next. Highest response ratio next. This is the CPU scheduling algorithm. So as the name suggests, highest response ratio next, that means we are going to schedule first those processes, or that process which is having the highest response ratio. We are going to schedule that process which is having the highest response ratio. Now how to find response ratio? Response ratio is nothing but a waiting time of that process till that unit of time, or till current time, plus the burst time of that process divided by the burst time of same process, right? So WT plus BT divided by BT. Waiting time plus burst time divided by burst time is going to give you the response ratio for that particular process. CPU is assigned to the process having the highest response ratio, and in case of a tie, it is broken by FCFS. Operates only in non-preemptive mode. So keep this in mind, this is non-preemptive in nature. That means once you allocate the CPU to any particular process, so until its completion you cannot preempt that process. Okay, first it is going to complete the execution, and then you are going to give the CPU to any other process. What is the advantage of this algorithm? It performs better than shortest job first. It not just favors the shorter jobs, but also limits the waiting time of longer jobs. So based on response ratio, we are also going to reduce or limit the waiting time of the longer jobs. So that's why it's performed better than SJF in that case. What are the disadvantages? Cannot be implemented practically. Why? Because as it depends on the burst time, and burst time cannot be known in advance. Okay, so now let's solve one question based on it, and we will be getting more clarity how it schedules the processes. So we have five processes here: P0, P1, P2, P3, and P4. Arrival time and burst time is given to us for all these processes. So let's schedule it. Now carefully see, at 0 units of time, do we have any process present in the ready queue? Yes, we have P0 process present in the ready queue at 0 units of time. So only one process, non-preemptive in nature, we are going to schedule until its completion. Okay, till its completion we are going to schedule it. So we have P0 here. For 3 units of time we are going to schedule it. So P0 has completed its execution. At 3 units of time, we have again only one process present in the ready queue, that is P1, right? So again we can schedule P1 process here till its completion. For 6 units of time, 3 plus 6, it is going to be 9. We can make it 0. P1 has also completed its execution. Clear? Now at 9 units of time, we have 3 processes present in the ready queue: P2, P3, and P4. Clear? Because the arrival time is less than 9 for all these 3 processes. That means all the 3 processes have arrived in the ready queue. Now we need to find the response ratio in order to decide which process will be given the CPU next. Okay, so let's do the calculation here. For the first time, we are going to find response ratio for P2 process. So I'm just writing it like RR2, response ratio 2. What is, so we have the formula here: response ratio is waiting time plus burst time divided by burst time. Clear? Now this response ratio for the second process, waiting time, how we are going to find the waiting time? So now at 9 units of time, if you see, P2 process arrived at 4 units of time. So what is the waiting time of P2 process at this point of time? It is going to be 9 minus 4 plus the burst time, that is also 4, divided by the burst time, which is 4. If you calculate it, 9 minus 4, it is 5, 5 plus 4, it is 9, and 9 by 4, and that will give you something around 2.2. Correct? Yes. So it is going to give you 2.2 something, right? Then we are going to find the response ratio for the P3 process. So what is going to be the waiting time for P3 process? 9 minus 6. 9 minus 6 plus the burst time of P3 process divided by the burst time of P3 process. 3 plus 5, it is going to be 8 divided by 5, and this is going to give you 1.6, right? What about P4 process? Again, 9 minus 8 plus 2 by 2. So it is going to be 3 by 2, and it is going to give you 1.5. So which process at this point of time, which process is having the highest response ratio? You can find it out. P2 process is having the highest response ratio, so we are going to schedule that process first. Clear? So let's schedule P2 process now till its completion, because it is non-preemptive in nature. So we are going to schedule it for 4 units of time. 9 plus 4, it is going to be 13. We can make it 0. P2 has also completed its execution. Now we have 2 processes, P3 and P4, and again we are going to find out the response ratio for these 2 processes. So I'm writing like RR3, that is for P3 process. So what is the waiting time of P3 process? Now at 13 units of time, if you see, P3 arrived at 6 units of time, so waiting time is going to be 13 minus 6 plus the burst time, that is 5, divided by 5. So it is going to give you what? So 13 minus 6, that is going to be 7. 7 plus 5, it is going to be 12. So 12 by 5, and it is going to give you 2.4. Similarly for P4 process, so 13 minus 8 plus 2 divided by 2. So it is going to be 7 by 2, which is going to be 3.5. So you can clearly see that process P4 is having the highest response ratio at this point of time. Clear? So we are going to schedule P4 first till its completion. So 13 plus 2 is going to be 15. We can make it 0. P4 has completed its execution. And now we have just only one process present in the ready queue, so no need to find the response ratio. We can clearly schedule that process now, P3, till its completion. So 15 plus 5, it is going to be 20. We can make it 0, and P3 has also completed its execution. Clear? Now we can write the completion time of all these processes. For P0 it is 3, for P1 it is 9, for P2 it is 13, for P3 it is 20, and for P4 it is 15. We can find the turnaround time, and turnaround time is nothing but completion time minus arrival time. So 3 minus 0, it is going to be 3, 9 minus 2, it is 7, 13 minus 4, it is 9, 20 minus 6, it is 14, 15 minus 8, it is going to give you 7. Clear? Now waiting time is what? Waiting time is turnaround time minus burst time. So 3 minus 3, it is 0, 7 minus 6, 1, 9 minus 4, it is 5, 14 minus 5, it is going to give you 9, and 7 minus 2 will give you 5. Now you can find out the average turnaround time by adding all these turnaround time of all the processes divided by the number of processes. Similarly, you can find the average waiting time as well, which they are going to ask you in the exam. Okay, so in this way we need to find we need to schedule the processes using HRRN, highest response ratio next. And at every point of time when you have more than one process present in the ready queue, you need to find the response ratio for all those processes, and then you need to compare the process which is going to have the highest response ratio. Next you are going to schedule that process first. Okay, so let's proceed further to our next CPU scheduling algorithm, which is very important, round robin scheduling. And most of the time you will be getting question based on this in the exam. Okay, so let's understand what is round robin scheduling. So let's see here. CPU assigned to the process on the basis of first come first serve, but for a fixed amount of time, that is time quantum. So if you remember, in first come first serve we just simply schedule the process, and that is non-preemptive in nature. So whichever process comes first, arrives first in the ready queue, we are going to schedule that process first. It is also based on FCFS, but here it is preemptive. It is preemptive. And there is some fixed amount of time, that is the time quantum, which is already decided that okay, for this time quantum we are going to schedule the processes. Okay, after the time quantum expires, the process is preempted and is sent to the ready queue, and it is always preemptive in nature, so as we have already discussed. Round robin scheduling is FCFS with preemptive mode. I hope it is clear now. Now let's understand the flow of round robin scheduling. So we have the ready queue. That means we have the processes in the ready queue. Okay. Now we are going to select a process based on first come first serve. So let me write here also, based on FCFS we are going to select the process. Now we are going to compare the burst time of a selected process with the time quantum. So let's say for time quantum is X units of time. Okay, so here first we are going to compare whether the burst time of selected process is less than the time quantum. If yes, then we are going to schedule that we are going to execute the process till completion. Okay, if burst time is less than time quantum, we are going to schedule the and execute the process till completion. Clear? But if the burst time is greater than time quantum, then we are going to execute the process for that unit of time quantum. That means for x units of time quantum only, not entirely. Okay, then we are going to preempt that process, and if process executed completely, then it will go to the termination state. Otherwise it is going to go back to the ready queue, so that again it can be picked, or any other process can be picked based on the arrival, based on the order of arrival. Okay, so this is going to be the flow chart of round robin. You will be getting more clarity when I'm going to solve the question based on this. So before solving the question, let's understand the advantages and disadvantages of round robin scheduling and few more concepts related to it. So it gives the best performance in terms of average response time, right? So average response time, why it gives the best performance in terms of average response time? Because the process which arrives, it doesn't have to wait long, because we have a fixed time, fixed amount of time, that is the time quantum, and after certain units of time quantum, the other processes are also going to get the CPU. First time allocation of CPU will be there as soon as your process arrives in the ready queue. So that's why the average response time is going to be better in this round robin scheduling. It is best suited for time sharing system, as we are using a time quantum, so that's why it is best suited for time sharing system, client server architecture, and interactive system. Clear? What are the disadvantage? Large waiting time and response time. Average response times is going to be good, but if we compare just for a particular process, it is going to have a large waiting time, low throughput, context switches will be there, more context switches will be there. Okay, based on the time quantum. So let's understand this point here. With decreasing a value of time quantum, with the decreasing value of time quantum, the number of context switches increases. So let's understand this. If you decrease the time quantum, okay, that means your a particular process will be executed for less amount of time. Clear? If a particular process is going to execute for less amount of time, in that case, your process will get preempted and another process is going to get scheduled. Then that second process will also be executed for that amount of time, and then it is going to get preempted, then another process is going to get scheduled. So if you decrease the value of time quantum, the number of preemption will happen, the number of preemption will increase, and we can say basically the number of context switches will increase. So if time quantum you are decreasing, context switching will increase. And response time is going to decrease. Obviously that is true. If you are having less time quantum, you will be scheduling all the processes quickly one by one, and the response time will decrease. That means the first time CPU allocation will decrease, okay, if you are having less time quantum. And chances of starvation also decreases, because every process is going to get its chance to execute in lesser time. Now there are some other points also. If you increase the time quantum, what will happen? That means you are giving more amount of time for a process to execute. In that case, what will happen? In that case, context switches, number of context switches will reduce, right? Because now you are not preempting the processes just after a certain unit of time, or just few units of time. You are giving more time to a process to execute. That's why context switches will decrease, the preemptions will decrease, right? Now smaller time quantum is better in terms of response time, and that I have already explained in the previous slide. If you are having smaller time quantum, response time will reduce, right? Response time will reduce. Higher value of time quantum is better in terms of number of context switches. So as I explained here, if the time quantum is higher, number of context switches will be less. Then with increasing value of time quantum, round robin scheduling tends to become FCFS. This is also true. If you are increasing time quantum, if you are giving more amount of time up to a process to execute, then it is nothing but it is going to behave like FCFS. And when your time quantum is, let's say, very huge, tends to infinity, then in that case your round robin will become FCFS. Okay, your round robin algorithm will become FCFS. Whichever process arrives first in the ready queue, you are going to schedule it almost, we can say, till its completion, if time quantum is very huge. And value of time quantum should be neither too big nor too small, so we have to decide properly what should be the optimal value or for time quantum, so that we can have a balance between uh, both the context switches and the way we are going to schedule the processes. Okay, so it should not be too big and it should not be too small as well. Now let's solve one question based on round robin scheduling. So we have here five processes given to us. Time quantum value is given to us, that is 2 units of time. So burst time and arrival time is given. We need to find the completion time, turnaround time, and waiting time for all these processes. So carefully understand this, because round robin is very important. And if you understand this one example, you will be able to solve any other question based on round robin, I can say for sure. Okay, so this is the Gantt chart through which we are going to schedule the processes. And here we have one queue as well. Okay, we have one a ready queue. We maintain a ready queue separately just to make sure that we are scheduling the processes correctly. Okay, so let's see here carefully now. At 0 units of time, do we have any process present in the ready queue? Yes, we have P1 process present in the ready queue at 0 units of time. So we have P1 process present in the ready queue at 0 units of time. So we can schedule P1 process first. Okay, we can schedule P1 process. Now we are going to compare time quantum value with the burst time. So you can clearly see time quantum value is less than the burst time. So we are going to schedule the process for 2 units of time only, not for 5, because if time quantum value is less than burst time, you are going to schedule the process for time quantum, whatever is the value. We have already seen in the flow chart in the previous slides, right? And if burst time is less than time quantum, then we are going to schedule it for burst time, whatever is the value, right? Now for 2 units of time, we are going to schedule P1. So 5 minus 2, it will become 3. Now clearly, carefully see here, at 2 units of time, do we have any other processes arriving in the ready queue? So we can say yes, P2 is there. So we are going to write P2 first. Yes, P3 is also there. So we are going to write P3 first. P4, no, P4 will be arriving at 3 units of time. Fine. And P5 is also not going to arrive now. It is going to arrive at 4 units of time. Now we have scheduled P1 process already. Now we are going to DQ P1 process, and we are again going to NQ the P1 process. That means we are going to again insert the P1 process. Now carefully see here this line, FCFS with preemption. In queue, first add processes which has come or which has arrived in the ready queue. First you have to schedule those processes first, and then add the concerned process if the burst time is remaining. Now in this case, if you carefully observe, at 2 units of time, first we inserted the processes which have arrived. So P2 and P3 arrived. So first we scheduled those processes in the queue. Okay, we maintained the order of those processes in the queue, and then we inserted P1 after dequeuing it or after removing it from queue. Clear? Now we have next process as P2 that can be scheduled, because as based on the ready queue we are going to schedule the processes. Now P2 is having the burst time 3, time quantum is 2, so whichever is less we are going to schedule for that amount of time. So 2 plus 2, it is going to be 4, 3 minus 2, it is going to be 1. At 4 units of time, we can say P4 and P5 both have arrived. So first we are going to write P4, then we are going to write P5, and then P2 we have scheduled, so we are going to remove it, and again we are going to insert it. So this is very important. Most of the students, they commit mistake here. First you have to insert those processes which have arrived, and then you have to insert that process in the queue which is which for which the burst time is still remaining and you have just executed now. Okay, so now we can schedule P3 process. So P3 is next, so we can schedule P3 now. So for P3, burst time is 1, time quantum is 2, whichever is less you are going to schedule for that amount of time. So that is 1, 4 plus 1, it is going to be 5. We can make it 0. P3 has completed its execution. So we are just going to remove it from the queue. Okay, and all the other processes have arrived. So let's proceed further with the P1. So for P1, burst time is 3, time quantum is 2, whichever is less we are going to schedule for that amount of time. 5 plus 2, it is going to be 7. 3 minus 2, it is going to be 1. Now we have scheduled P1, so we can remove it, and again we can insert it because still 1 unit of time is remaining for P1. Now it's turn for P4, so we can schedule it. P4, time quantum is 2, burst time is 2, so we can schedule it for 2 units of time. 7 plus 2, it is going to be 9. We can make it 0. P4 has completed its execution. We can remove it from the queue. Now we have P5 process that has to be scheduled next. P5, burst time is 3, time quantum is 2, whichever is less. That means time quantum 9 plus 2, it is 11. We can make it 3 minus 2, it is going to be 1. We have scheduled P5 process. We can remove it and we can again insert in the queue because 1 unit of time is still remaining for P5. Now it's turn for P2. So for P2 it is 1, time quantum is 2, whichever is less. That means here in this case burst time is less, so we are going to schedule for that amount of time. 11 plus 1, it is going to be 12. We can make it 0. P2 has completed its execution. We can remove it from the queue. Clear? Now we have P1 process, so let's schedule that now. So for P1 it is again 1, time quantum is 2, so 12 plus 1, it is going to be 13. We can make it 0. P1 has completed its execution. We can remove it from the queue. Now we have only P5 process left, so burst time is 1, so 13 plus 1, it is going to be 14. We can make it 0. P5 has completed its execution as well. So in this way we are going to schedule the processes based on round robin scheduling. We can find the completion time, scan from the right hand side, right to left. For P1, the completion time is 13. For P2 it is 12. For P3 it is 5. For P4 it is 9. Right, and for P5 it is going to be 14. Turnaround time, completion time minus arrival time. So 13 here, 11 here, 3 here, 6, 14 minus 4, it is going to be 10. Waiting time, turnaround time minus burst time. 13 minus 5, 8. 11 minus 3, that is also 8. 3 minus 1, it is 2. 6 minus 2, it is 4. 10 minus 3, it is 7. Now we can find the average turnaround time, average waiting time for all, for after scheduling the processes. So you can just you can just add them up and divide by the number of processes. Clear? So these type of questions can be asked in your exam, and carefully observe how we are scheduling the processes in round robin. Sometimes students make mistake, so it's very important. This point is very, very important. Okay, try to solve this question again and try to solve some other questions that has already been asked in the GATE exam previous years. Okay, so that's it from this lecture. I will be covering the remaining CPU scheduling algorithms in the upcoming lectures, and you can join our MindMatrix channel on WhatsApp. This is the link, and the link is also given in the description, also on our YouTube channel for both WhatsApp and the doubt discussion Telegram group. You can also join doubt discussion Telegram group using this QR code. You can just scan it and you will be able to join it, where you can ask your doubts. We are also sharing the PDFs of our lectures. You can join, you can download that, and you can make notes. Okay, and guys, do like this session, subscribe to our channel MindMatrix, share with your friends, those who are preparing for GATE 2024 and GATE 2025. share with them, and like the session. Okay. So thank you everyone. We'll see you in the next lecture. Thank you. Bye bye.